So for day 3 of chapter 11, we're going to begin looking at our next type of conic, which is an ellipse. So we're going to start by first looking at a few different graphs of ellipses and try and connect the graph of the ellipse to the equation of the ellipse. So you look at number 1. An ellipse should start there, I guess, is for lack of a better word, a non-mathematical definition is it's really just an oval. So there are specific properties about an ellipse that we will identify, but in general, it is a oval-shaped conic that has a center, and we will identify some of the information about it based on the equation. So first thing I want you to notice is that, again, every ellipse has a center, and the center in this case in number 1 is 0, 0. And also, we should be able to see that from the center to the edge of my ellipse horizontally, in this case for number 1, is a distance of 2, which, if you look at the equation, there's a 4 in the denominator of my x variable, which is very closely related to that number. And I'll kind of identify that, formalize that relationship here in a second. Then if you look from the center to the edge of the ellipse vertically, that is a distance of 3, and that seems to be closely related to my denominator of my y variable. So the idea here is, and we'll check that it is true in number 2 as well, but from the center to the edges of my ellipse, there is a distance, a number that is related to the equation. So the number underneath x in the equation is 4, and then that is the square root of 4 is 2, which is the distance from the center to the edge in the x direction, left and right. And then the square root of 9 is 3, and the distance from the center to the edge of the ellipse vertically in the y direction is 3. So that's really what those denominators definitely identify for us. Now let's make sure that that relationship holds in number 2. The only difference in number 2 is the center is not at 0, 0, but we can still think of from the center to the edge, and we'll get more formal with our definition here in a second, but from the center to the edge should be related to the denominator. So first thing I do for number 2 is look at the center. In this case, the center is negative 3, 2, and to find the center, it's going to follow the same rules for function transformation stuff we've talked about this year, and also the same type of identifying coordinates as we did with parabolas. Because it's x plus 3 quantity squared, then the x coordinate of the vertex, or excuse me, x coordinate of the center should be negative 3, and because it's y minus 2, the y coordinate will be 2. So the center is negative 3, 2, and then if we were to look from the center to the edges of the ellipse horizontally, the distance there should be 2, which is the square root of 4. And then from the center to the edge of the ellipse vertically is a distance of 5, which is the square root of 25. So again, that relationship with the denominator of our variable and the distance from the center to the edge is going to be vital for graphing ellipses for sure. So the couple other things I want you to identify about the equations is, for a standard form ellipse, the equation will always be equal to 1. So if it's not equal to 1, we will have to rewrite it so that it is, and we'll see how to do that in the notes for today, for day 3. And also, both variables are squared, x and y. Now obviously it could be a quantity of x plus 3, y minus 2 in the second example, but there's always an addition between them. And that's going to be one of the identifying characteristics of an ellipse versus other types of conics, is that we have both variables being squared and they're being added together. That is specifically an ellipse. So what we want to be able to do here is just take an equation and sketch the graphs. And then once we have the graph sketched, I'm going to identify a couple vocabulary words that are specific to ellipses. So if you look at number 3, we have y squared is written first, and pay attention to that. Again, it's addition between there, so I can write my x variable term first or my y variable term first. But the number in the denominator will matter in terms of how to graph this. So the center of this ellipse is going to be 0, 0, because x and y are not being shifted left or right at all. And then the denominator of y is 81. And what that tells me is, again, I'm going to graph my center and then the denominator of y is 81, which means the square root of 81 is 9, and that will be the distance from the center to the edge of the ellipse vertically, or in the y direction. So you can see plotted my center and plotted a point 9 units above and 9 units below, and that's comes directly from the 81 in the denominator of my y term. And then for the x term, the denominator is 16. So if I take the square root of 16, I get 4, and I should graph the other edges of my ellipse, endpoints, however you want to think about them, 4 units to the right and 4 units to the left. And then I should be able to just sketch my ellipse and try and be careful here to make it look like an oval. Try to resist coming to a point, or just not being careful that it looks symmetric on either side of the center. So that's number 3. Again, identifying the center will be helpful obviously first, and then using the denominators of my y and x variables, that's how I'm going to decide how far above and below the center and how far left and right of center I should graph. So for number 4, I'm going to first identify the center, and the center is going to be 2, -4. So I'm going to plot that point. And then 36 is the denominator of x, which means the square root of that is 6. So I should graph left and right of center 6 units. So 6 units to the right, 6 units to the left. And there's a name for those points that we'll identify here in a second. And then the denominator of my y variable is 9. So the square root of 9 is 3. So I should go 3 units above and 3 units below the center. And there's my ellipse. So that is what the graph would look like. And then there's a couple specific vocabulary words that we're going to identify from that are specific to an ellipse that we didn't talk about or explicitly talk about for parabolas. So for ellipses, there are a few specific vocabulary words that we're going to identify right here before we move on to the notes and practice using those vocab words. So we've already talked about the center. So really every ellipse has a center. Every ellipse has also, the word we're going to use is vertices. So for a parabola we had a single vertex, but for an ellipse, what it looks like now, if you look at an ellipse, we really plot 4 points to kind of get the shape of the ellipse, but the vertices are going to be 2 specific points on the ellipse. So in terms of a working definition of a vertex, or vertices in this case, the way I'm going to describe it is it's going to be the coordinates of the ends, and when I say ends I mean just kind of the edge of the ellipse, in the direction where the ellipse is widest. So what that means specifically is if you look at number 3, the vertices would be the coordinates of the point at the top and bottom of the ellipse, because the ellipse is a distance of 9 vertically in either direction, so those endpoints will be my vertices. And for number 4, the vertices will actually be the endpoints left and right of center at the edges of the ellipse, because that's the direction that the ellipse is widest in. And it will always be related to the denominator of the variables that we were dealing with in the equation, because obviously that's how we count how far we go in what direction. But specifically, the 2 we're going to identify are the ones at the wider ends of the ellipse. So for number 4, if I wanted to identify the vertices, it'd be the coordinates at the edges here horizontally, so it should be 6, -4, and sorry, not 6, -4, should be 8, -4, and the other vertex would be -4, -4. And then if you look at number 3, in terms of identifying the vertices, there would be the coordinates of the endpoints at the top and bottom of the ellipse, which in this case would be 0, 9, and 0, -9. And then the other thing we need to talk about that is specific to ellipses are same idea we talked about with parabolas, in that a parabola had a focus, but an ellipse has 2 focuses, or the word for that is foci or foci, however you want to pronounce that. And in terms of a working definition of foci, they are fixed points, and then in terms of how far away those points are, the variable we use for that is c, and we will talk about how to find c, but we can say the foci are fixed points, c units away from the center, always between the center and the vertices. So again, if you look at these examples here for 3 and 4, we have our center, we have our vertices at the ends of our ellipse. The focus should be a point somewhere in between the center and the vertice on each side. So we'll look at how to find that in a second, but again, if I just kind of sketched something in terms of a foci for number 3, I don't know specifically where that point is yet. We will find that, but it is some distance from the center towards each vertex, but somewhere before it. So it's going to be, somewhere in between there. We'll find the exact values, but again, each ellipse has 2 foci in between the vertex and the center on either side of the center. So then if you look at number 4, similarly, we will have a focus on either side of the center. C units, whatever C is, we'll learn how to find that. But again, the foci points should be somewhere between the vertices and the center. So we will look at how to find those, and it's definitely related to the numbers in the denominator, how we counted the distance from the center to the edges of the ellipse.